Section 28, natural log derivatives and integrals. So this is a pretty simple section as what's specifically assigned to this section. It's basically just that natural log's derivative is 1 over x, and if you go the other direction, if you start with a 1 over something, you get back to a natural log. This is ocelot danger land, because a lot of people see a situation like, hey, the integral of 1 over u squared, and they go, oh, it's 1 over something, I can use natural log here. But actually, this isn't a case where you use natural log at all, because we can rewrite this as u to the negative 2 du, raise the power by 1, divide by the new power, plus c, and that's our answer. No natural logs. Now if we took the integral of this again, so a second integral, very exciting. Well, I'll rewrite it as negative u to the negative 1 plus c. Well, now when I integrate this, I have to get a natural log because I have just 1 over u, or u to the negative 1 here. So now I get negative natural log of u plus c. So here I didn't need it because I had 1 over something squared, and here I did need it because I actually had 1 over something. Okay, so why is there an absolute value in my answer? Well, let's talk about that real quick. So here I have 1 over x, which is the thing we're integrating. So this is like our derivative graph, and our derivative graph of 1 over x has values defined for x is greater than 0 and x is less than 0. It's undefined at x is equal to 0. It's discontinuous, infinite discontinuity here. So we need to have an integral that's defined for both this stuff and this stuff. And why natural log of x isn't good enough is this is what natural log of x looks like. It doesn't exist for x is less or than or equal to 0. So let's first convince ourselves that this is a legit graph. Like, this thing's derivative is like super duper duper positive steep, and then it starts flattening out, flattening out, flattening out. Super duper positive, flattening out, flattening out, flattening out. So the derivative matches. And if you're still practicing drawing derivative graphs, this is a good example of one where it like really makes sense. So if we throw the absolute values on the thing in the inside, all of a sudden every x value we're putting in is positive, which means we get this thing reflected on the other side, and we get it defined for every value. Let's see if these actually match. Okay, so again, this is our derivative. So we should have like a really, really negative slope and then flatten out. Really, really negative, flatten out. Yep, we're good. So yeah, negative slope over here, negative slope over here. It matches up. Okay, so that's the reason why we have the absolute value. So you always need to have the absolute value when you integrate 1 over x. We don't need the absolute value in any other case. 1 over x, if we think about derivatives, like the derivative of natural log of x, if I don't have an absolute value, it is 1 over x, but it's technically 1 over x only for x is greater than 0 because natural log of x doesn't exist for x is less than 0. So we can kind of just rule it out. Whereas if we take the derivative of natural log of absolute value of x, then we just get 1 over x unconstrained because neither of them exist at 0, and we now have negative values. All right, let's just look at some examples. So these are the two off my website. Oh, natural log inside of a natural log. This is going to be horrible, right? Not really. So looking up at our rule up here, du over u, the derivative of natural log is du over u. So we're going to do a du over u. So du is going to be on top, so that is the derivative of this stuff. So 2x minus 3x squared plus 1 over x, which is the derivative of natural log of x. And our u is just the inside, not the derivative of the inside. So we get x squared minus x cubed plus natural log of x. Let me write that a little cleaner. X cubed. That's not cleaner. If you're like, wow, this is way too much all at once, just think about it this way. 1 over whatever is on the inside of the natural log times the chain rule of the inside. And that's the same thing. All right, that's it for natural log derivatives. There are a few things I could add here. So just a quick go over of things I could add here is I could make you take the derivative of natural log of, let's do something creative here, like the square root of x plus 7's cubed. And you're like, oh, this looks horrible. The inside's going to have like chain rules and stuff. No, there's a shortcut. Ooh, let's even change this up and make it even a little bit harder. Let's throw an x in there. So, still a shortcut here. We can split this into two integrals. Actually, no, let me pull out the square root first. 1/2 natural log of x times x minus 7 cubed. If you're like, how did I pull that out? It's the power of the inside. You're allowed to pull the power out of the on the inside out in front of the natural log. If you want to see more on this, I have a video in my algebra review for calculus section. All right, next step is I can split this into two integrals. I can have 1/2 of the natural log of x, because things that are multiplied we can split into two integrals, plus 1/2 the natural log of x minus 7 cubed. Okay, now I can just pull out this power, so I'm just going to do that by erasing and doing this. That was easy. It was the entire power of the inside, so that's totally legal. And now I'm ready to take the derivative. It's going to be 1/2 times 1 over x, because the derivative of natural log is just 1 over x, plus 3/2 times 1 over x minus 7. And that's it. That was the derivative step. So it's often very useful to simplify something before we integrate or divide or take the derivative. All right, let's look at integrals now. A little more complicated. In integrals, we very often have du over u sort of situations here, which means we have to use u substitution. So in both of these, we have to use u substitution. So on the left side, our u is just the bottom, 7x minus 6. So our du equals 7 dx. Whoops, dx. And then our right side one, u equals, well, actually, let's call it something different, so we don't have double u's that are different. V equals 2x minus 1, and dv equals 2 dx. Okay, now I'm going to write this as two integrals, so I'm going to write this as the integral from 1 to 2 of, well, my 14 doesn't really change here, so I'm going to have 14 over u, and then instead of dx, I'm going to plug in what dx is equal to. So I didn't solve for it here. Dx is equal to du over 7, so I'll plug that in, times du over 7. So that's one of my integrals. That's for the first part. And I'm going to add to it the integral from 1 to 2 of the second part. So here, I should have also solved for dx here. So dx equals dv over 2. So I'm going to have 1 over v, yeah, it looks fine, times dv over 2, which I plugged in for dx here. So I split this into two integrals and plugged in my variables. Now let's simplify this real quick on the right side here from 1 to, or left side. 14 divided by 7 is just 2. So this is 2 over u du. This guy I can also simplify. Integral from 1 to 2 of dv over v, and we have a 1/2, and I'll just pull it out in front. So it should be pretty easy to integrate these. We just get 2 natural log of the absolute value of u, evaluated at 1 and 2. And here we get 1/2, also evaluated at 1 and 2, of the natural log of v. Oh, and I'm going slightly off the page here. All right, now we've integrated. We need to plug back in u and v. So 1 to 2 of 2 natural log of 7x minus 6. And integral from 1 to 2 of 1/2 natural log of 2x minus 1. And lastly, all we have to do is plug in our values. So I'm going to do that over here. So if I plug in 2, I get 14 minus 6 is 8. So I get 2 natural log of 8. Minus, because I have to subtract the bottom term. If I plug in 1, I get 7 minus 6, 1. Natural log of 1, or log base anything of 1, is 0. So I'm just not even going to write that term. And I'm just going to add, with 2 plugged in this one, I get 4 minus 1 is 3. So I get 1/2 natural log 3. And with 1 plugged in, again, I get natural log of 1 in the inside. It's 0. And so that's our answer. And that's it for natural logs.